Good afternoon.
Hello.
Hello there.
Well, thanks to all of you who let me know you could hear me. I appreciate that. I'm at the present time, I'm not really starting. I'm just doing something here because I don't think the diagram is as clear as it could be on the notes. So I'm just kind of redrawing it. No, I haven't started yet, folks. Don't panic. All right, folks, it's 12:30. We'll get started here. So I was just redrawing this diagram to make things a little bit clearer as to what was going on here. The diagram I have here it's okay, but there are things about it that are kind of perhaps a little bit not great. All right, So I'm going to go ahead here and get started. So what we're looking at here, I'll go back to the initial notes. We're looking at a competing reaction of a diene here. And in the course of this reaction, you can see that we have an HBr that's under low temperature conditions, minus 40 degrees. And then we have HBr at 80 degrees. So we have low temperature and we have high temperature. Now, what you can see there is that at those temperatures, the different temperatures, we get different distributions of the two expected products from the addition of HBr to the double bond. Now, the mechanisms for those are shown here, and they're also shown on the next page as well. I've kind of just transposed them over. It's just that they weren't incredibly clear on the slide, so I redrew them over here, especially the second one, with what's going on with those arrows. All right, so in the first one, you'll notice that we have H plus joining to the double bond. Now, generally, the pattern with that kind of mechanism is that the H goes on one side and the plus goes on the other. Now, when you're determining which side the plus goes on, you've got to think, well, which cation would be more stable? So a little bit of background here, and I'm just going to put that here, and I'll erase it after I get done. Let me change the color here. There we go. So just a reminder, we've actually talked about this back in test 1, we talked about it. About tertiary C pluses being more stable than secondary. And that's more stable than primary. Now you can see the difference between the three situations. The tertiary has 3 carbons connected to the C with the plus. Secondary has 2 carbons connected to the C with the plus. And primary has 1 carbon connected to the C with the plus. And there's a whole thing with hyperconjugation. I don't really want to get into that again, but just tertiary is more stable than secondary is more stable than primary. If you need more information about that, you can go back to test 1, where we talked about carbocation rearrangements, and it'll give you a primer or a little bit of a reintroduction to carbocation stability. Does anybody have any questions so far? So the other piece of information that you need to be aware of here, I'll move this over a bit, has to do with the notion of double bond stability. So back in Organic 1, you would have remembered, or you might not, I don't know. But there was something called the Zaitsev rule, which basically means that more substituted double bonds are more stable. Now, what do I mean by that? I mean, the more carbons there are attached to a double bond, the more stable it is. So the Zaitsev rule basically says that this situation is the most stable, followed by this one, followed by this one, followed by this one, followed by this one. So in each case, what I'm doing is I'm starting out here with 4 C's connected to the double bond, and then 3, then 2, then 1, and then none. So the more substituted the double bond is, the more stable it is. Part of it's steric, part of it has to do with, and when I say steric, I mean part of it has to do with the fact that there's stuff all around the double bond, which makes it less accessible, less reactive, which makes it more stable. I think that's the main reason. The other thing, there might be a little bit of something from hyperconjugation, a bit of interaction between the double bond and the electrons in CH, adjacent CH bonds. It's possible, but I think most of it has to do with the number of carbons directly connected to the double bond. Does anybody have any questions so far?
Yeah, so if we had, for the one that has 2 carbon attached to the double bond, if we had cis, would that fall before or after the trans that you drew?
I think it would kind of fall pretty much, maybe a little bit after, because there would be a little bit of interaction. I actually made a mistake here in this diagram. Let me fix it so it makes more sense. There we go, it's better. So then we can talk about this in terms of energy diagrams as well, and we can begin to see why we might get the product distribution we do. So remember, it all comes back to this. Low temperature, we get 80% of the first one and 20% of the second one. And in the case of the high temperature, we get 20% of the first one and 80% of the second one. All right, does anybody have any questions so far? So when drawing an energy diagram for this, the pink one is going to be this one. I'm going to call this one pathway A, because that's what I've done in the diagram. So this is pathway A. The pink one. And this is pathway A up here. And the black one is going to be pathway B. Okay, so let's look at how we interpret the mechanism in relation to the energy diagram. So when we're looking at the pathway A, you can see the first step is the H plus joining onto the double bond. The plus goes on the more substituted carbon, the secondary one, as opposed to the one on the end, which would be primary. And then we get the Br compound that you see here. In pathway B, we have the H plus join onto the double bond, and then we get resonance occurring where the double bond can actually move to the end, the middle here, and the plus moves to the end, and then the Br attaches to the end, resulting in the product that is the result of B. So at the beginning of the energy diagram, what's present is just the reactants, and that's why they start in the same place. So this and this that are at the beginning are representative of what's happening at the beginning of the energy diagram. That's the first thing. So if energy changes occur, something reacts, and then we get this energy well. This well here is the intermediate. So it's this part of the diagram right here. So that's what goes in the energy well, here and here. And the products here, whoops, start again. The products, of course, are going to represent what's happening at the end of the energy diagram. And since I've got the black pen already here, I'll go ahead and label some of these. The product of pathway B, what I've called the black pathway, is this one. And the intermediate in pathway B is going to be this one. Now I'll go back to pathway A, and the product of pathway A is this. It's going to be, it's going to have the Br and the double bond here on the end, and the intermediate here will be pathway A. Sorry, I actually mixed those up. I'll erase that and I'll start that again. Pathway B is this one with the one on the end. Oops. But I'll do pathway A first since I've got the pink pen here. There we go, that's better. And I'll get the black pen. Now we'll do this one. Okay, this is why I had to make the correction. There we go. Now what you can see here, and this is kind of the entire point of all of this, is that if you compare the two carbocations, you'll notice that the pink one is more stable than the black one. And the reason is because the pink one is secondary and the black one is primary. That's why the energy well here for pathway B is higher than the energy well for pathway A. Does anybody have any questions about that? Let me see if you understood that statement about why one of these is more stable than the other, why the pink one is lower energy than the black one. Okay. 5, 4, 3, 2, 1. Okay. All right. So we have one person who has no idea what's going on. We have, let me see. Sorry, share results. And 5 who halfway understand, 11 who understand. Are there any questions that can help out here? Especially for the person who has no idea what's going on, there must be some question you have that could clear things up. Not that I'm pointing that person out, because now that person doesn't want to ask a question because they think they'll be the one who doesn't have any idea what's going on. I don't want to label anybody here. But surely somebody must have a question, anybody. I mean, if that many people who halfway understand it or don't understand it at all, there must be somebody who has a question. Has it got to do with the telling which one's primary or secondary? Can anybody give me some guidance here? All right. I mean, if nobody's, I don't know if I can explain it any differently, but if somebody can clarify what they're having trouble with, then maybe I can bring this up here. All right. If we look at the end of the pathways and we're looking at the products, what you can see is that the black product here is lower energy than the pink product. And the reason for that is to do with the Zaitsev rule, because the black one is more substituted than the pink one is. And by more substituted, I'm talking about more carbons attached to a double bond. How do people feel about the products and their relative stability?
I didn't understand it.
Okay. Miriam, can you ask a question that would help?
So, okay, so you said the black one is more stable because there are more carbon attached to the double bond?
Yes. Okay, let me point to them.
Oh, okay, I see it. I see it now. So I was looking
one
at
here
and
one here, right? In the pink one, there's only one here. That's it. That's the only one attached to a double bond.
Okay.
So the comparison is like this and this. Anybody else has a question? All right, let me go on.
So the one that's higher energy is more stable. Is that what you're saying?
No, the lower energy ones are always more stable.
That doesn't make any sense to me because the pink is the lower energy, right?
No, listen. Look at the products, Julie. The products, just focus on the products.
Right. So
The black one is more stable than the pink one is, right?
Right. So the higher energy, it had higher energy, right? Because it's higher up here, right?
Look at the look at the graph, Julie. It's energy on this axis. Energy is going up, right?
Right.
The higher energy something is, the more unstable it is. So this peak here represents higher energy or less stability than this peak here.
On the ion, but the product is more stable.
Yes, that's correct.
Okay.
They switch, which is kind of the point.
Okay.
So you'll notice that the carbocation, the pink carbocation is more stable than the black carbocation, but the black alkene product is more stable than the pink alkene product. Is that okay?
Yes.
Okay. All right, let's see. And see how people feel about the products. Just the products. How do you feel about the products? The stability of the products. How do you feel about the stability of the products? Okay. 5, 4, 3, 2, 1. Okay. People feel better about that than they do about the carbocations. All right, so yes, as Julie was just intimating, yes, we get a switch here. You'll notice that the pink carbocation is more stable than the black carbocation, but the black product is more stable than the pink product. So what's going on here? Well, it all has to do with the change in temperature that we were talking about here. And this is what I want you to realize. When we're talking about this area, which I'm calling the intermediates, that's the middle area. Intermediates are the middle compounds in the process here. This is going to determine kinetics. And this has to do with activation energy. Now, the activation energy is going to be these two humps right here. So you can see that the activation energy for pathway B is higher than the activation energy for pathway A. So more energy has to be put in to get over the B hump than the A hump. I'll say that again. More energy has to be put in to get over the B hump than the A hump. I want to see if people understand that statement. How do you feel about that statement? Five, four, three, two, one. Okay. All right, so we're looking at, most people understand what's going on, but does anybody have any questions?
Yeah.
Yeah.
Why, if the carbocation on the black one is less stable,
Yes.
why does it need more energy to get over the humps?
Could you repeat that, please?
If the carbocation on the black hump B
Yes.
is
It is
less stable,
It's less stable, yes.
why
Yes.
does it take more energy to get over the humps?
Well, it's kind of because if you've got just think of this as stopping right here, Julie, right at the intermediates. Ignore the rest of it, okay? There's a law which I'm not really going to go into, which has to do with if you've got something of a certain stability and it's higher, then it's going to need to get more energy to get to that thing that needs that's lower stability or higher energy. You need more energy to get to something that's higher energy. I think it kind of makes sense in a way that it would take less energy to get to the lower energy carbocation and more energy to get to the higher energy one. Because it's higher energy, it's going to need a bigger hump.
Yeah, that makes sense.
Yeah, I'm glad you asked though, because that is a good question. Any other questions so far? All right, so that's with the intermediates, and that determines kinetics. And what I would say is that the pink one is the kinetic product. Right, lower activation energy. This is the kinetic pathway. So kinetics are determined by the activation energies. So lower activation energy, the kinetic pathway, which is pathway A. All right, I'm going to give you the other one here, and then we'll talk about the other part of this. The products, that's over here, whoops. The products are going to determine what's called the thermodynamic pathway. And that's based on product stability. So that's based on product stability. Now the one that's more stable is the black pathway. So most stable product and this is going to be the black pathway, and that's going to be the thermodynamic pathway, thermodynamic product. That's B. So A pathway A is the kinetic pathway. That's determined by the activation energy. And that is in turn determined by the cation stability. And then you've got the thermodynamic product, which is going to be determined by which one's more stable at the very end. All right, so let me try and explain these temperature distributions, sort of put this all into a neat little bow. So I've told you that the top one is pathway A. That's the lower temperature one. That's the low temperature pathway, pathway A. You'll notice that in order to get over this hump, we only have a low temperature. So most of it goes via pathway A because there's insufficient energy to get over pathway B. That's why pathway A is favored at lower temperature. Let's see how you feel about that. How do you feel about pathway A being favored at lower temperature? How do you feel about pathway A being favored at lower temperature? The pink pathway. All right. 5, 4, 3, 2, 1. Okay, so it's kind of the same proportion of people here. Can I get an idea of any questions anybody has about, you know, I mean, I'm trying to be as clear as possible about this, about pathway A being the relationship between activation energy and low temperature and high temperature. Any questions? A lot of people halfway understand it. I want to get you all to be a fully understand part. Any questions?
Could you explain it one more time?
Okay, so at low temperature, there's only enough energy to get over the pink hump. Remember, temperature and energy are kind of interlinked. The more temperature is, the higher the more temperature is, the higher the energy of the molecules, right? So the molecules are all going to be colliding faster and with more power at high temperature than low temperature. They move slower at low temperature as well. You okay with that, Miriam?
Yes.
So at low temperature, you can imagine that it's harder to get over the B hump, right? Because the molecules don't have enough energy to get over the B hump.
Right.
I mean, think of it like a ball being rolled up a hill. If you don't put enough energy into the ball, what happens? Mary, what happens if you don't put enough energy into the ball rolling up a hill?
Well, it would roll.
Rolls back down, doesn't it?
Right.
Yeah. So that's what's going to happen if you don't have enough energy. Say it can only get halfway up the B hump, right? It's just going to roll back down. But if it can get to the top of the A hump, it'll keep cruising. It'll go over the hump, right?
Okay. Can you, if I didn't have the energy diagram in front of me and I wanted to, based on the carbocation formation from the top, decide why pathway A is the low temperature, could I do that? Like, how would I figure it out?
What you do is you look at the relative stability of the carbocations, right?
Okay.
Because A is secondary and B is primary. So the secondary one's more stable, which means that it needs a lower activation energy to get to it. Did you hear me?
Yeah.
Miriam? That's really important. What I just said is really important.
Okay.
But I think that would help, wouldn't it?
Yeah, so the more stable carbocation, which is in this case a secondary over a primary carbocation, requires a less activation energy.
That's right.
Okay.
And you can see why, right?
Yes. Okay. Thank you.
Okay. All right. Any other questions? All right. Well, let's see if Miriam's question helped other people. I suspect it might have, but I'm not sure. Let's take a look. How do you feel about it now? About pathway A being the lower energy one and why? 5, 4, 3, 2, 1. See, Miriam, look at what you did. You did a public service. You see that?
Yep.
Yeah. See, this is why people should ask questions, because you don't know who you're going to help. You might not just be helping yourself. You might be helping a whole bunch of other people. Because I think a light bulb turned on for some people once I explained that to you and you got it, other people got it too. Yeah. There's a lesson there somewhere for somebody. All right. So let's talk about that. That gives you the kinetic product, which is A, or kinetic pathway, which is A. Same, really, it's really the same thing there. But when we're talking about the thermodynamic product, that's all going to be based upon the products. It's product stability. And as you can see, the black product is more stable than the pink product. Now, everybody said they understood that. They understood why. The black product is more stable than the pink product. But what that means is the thermodynamic product is going to be the black product, which is a result of pathway B. So pathway B is going to be the thermodynamic product. However, now let's talk about why that is. So what the idea here is that if you've got high temperature, it's kind of got a choice, right? You can go A or B. My theory here, but I'm trying to get to you to see, is that it'll take the route that will lead to the more stable product, because in the end, that's what nature wants. It always wants the more stable product at the end, if it can get there. If there's enough energy to get in, it'll choose pathway B over to pathway A, which means at higher temperature, we're more likely to get pathway B taken. Does anybody have any questions? So this is meant to explain these different percentages here. All right, how are you feeling about this so far? How are you feeling about it so far? 5, 4, 3, 2, 1. Okay. Does anybody have any questions? Okay, let's take a look at a test question. Any test question I give you is going to relate to this. It's going to have the double, a diene type core, but there's going to be other things connected to the diene. But the answers I'm looking for will be very similar, just applying that particular diene. So let's talk about that. Let's look at some questions, and we'll see. You'll see this. There we go. Let's take a look. All right, let's have a look. There we go. Here's a question here. And you can see that how it relates to what I've got on the screen. It's just got these squares attached at different places. They're not fill in the blank boxes or anything. They're supposed to be cyclobutane rings. Let's talk about the key and look at the answer that I'm kind of expecting here. Okay, so what you will do is, first of all, do the mechanism for the kinetic product, which is pathway A, and then the thermodynamic product, which is pathway B. And then you can see that this student did screw up something. I'm not sure what it is exactly. Oh, I think it had to do with the way they drew the energy diagram. I think the way the humps are, there was something suspect about the way they drew the humps. I can't rule out being a little bit too picky there. I might have been. Yeah, it's possible. But it could also be that they missed a charge or something somewhere as well. But yeah, I think that needs to be a little care taken to make sure that the energy diagram is pretty accurate. The first hump needs to be clearly bigger than the second hump, that's for sure. The first hump introduces a carbocation, so you're getting H plus adding to the double bond, which causes a carbocation, which is an unstable kind of compound. And then the negative, it's attacking the plus, is a low energy situation. Does anybody have any questions? Okay, so then the diagram was drawn. You can see what the students done, and they've labeled each of their relevant portions as A, B, C, D. The carbocations are A and C, the products are B and D. You can do it that way, or you can do it just by drawing them as well, or pointing to them like I've done over here. That's okay as well. But here you can see that the A is the tertiary carbocation and C would be a primary carbocation. So you can see why A would be more stable than C. And then if you look at the products B and D, you can see that D has a more substituted double bond than B does. That's 4 things around the double bond as opposed to 2, which explains the difference in the products there as well. Does anybody have any questions? All right, well, what I'm going to do is I'm going to challenge people to look at these, look at some more of these examples. I'm surprised nobody's asked me this yet, but does anybody have a request? I'm listening. No, nobody's brave enough to make the request. All right, I'm going to add a couple of old tests. All right, just like I did previously.
Yay!
Well, why didn't somebody make the request? If you don't ask, you don't get, right? What's the saying? Ask and thou shalt receive. In Australia, we put a little thing on the end of it. Don't and you bloody well won't. I heard that a lot as a kid. All right. Does anybody have any questions? Anybody got any questions? Okay. All right, I just want to check on something here. I just need to see how far I am supposed to get today. I know I was supposed to do this part. I just want to see other things as well. Let's have a look at syllabus. Nope, I don't want to do syllabus. I want to go to the mini lectures is what I want to do. There we go. That's better. Okay. All right. Alpha addition. Asymmetric. Okay. Let's take a look at the next portion then. I do have an explanation here as well. You can take a read of that. Pathway A is a favored process at low temperature because it has lower activation energy. This is the kinetic pathway. Pathway B forms a more stable product, the one with lower energy. The reaction effectively has a choice which pathway to take, since high temperatures provide sufficient energy for both activation energies of both pathways. The one that gives the more stable product will be favored. This is the thermodynamic pathway. So that's basically what I was saying earlier, but it is there as well in black and white. All right, so let's look at now reactions of alpha beta unsaturated carbonyl compounds. And when we're talking about alpha beta unsaturated carbonyls, a carbonyl compound is anything with C double bond O. Unsaturated means it has a double bond. Now, when we're looking at positions relative to a carbonyl group, we often use this kind of nomenclature, alpha and beta. I think I've gone through this before. I think we did this back in test 2. I talked about how with ketones and aldehydes, the position next to the C double bond O is called alpha, the one next to that is called beta. So this is alpha, beta, unsaturated carbonyl compounds. So alpha, beta, unsaturated, that's double bond, and there's your carbonyl compound there. And just for the purpose of numbering the grouping, we can number the oxygen as 1 and the end of the double bond as being 4. This is not like real numbering. Oh, by the way, there's no naming quiz for this test. I hear cheers in the background. So there's no naming quiz for this test. But in any case, this numbering I'm talking about has nothing to do with naming. It has to do with the positioning. So let's look at 1,2 addition first. Now, in this instance, what we're using is what's called an alkyl lithium compound. Now, an alkyl lithium compound, an example would be, let me show the example here. I put RLI, but the R can represent anything if you remember. Now, when you've got a lithium there, it's kind of like having a magnesium there. It's like a Grignard reagent. And you can really think of it just as being that. Hang on. 1, 2, 3, 4. That. There we go. So same number of carbons, just with the negative charge on the end where the lithium is attached. And the product of this happens to be this one. I'll go through the mechanism in a second here. The point being that the alkyl group is now attached to the carbon that's directly below the O. So we call that 1,2 addition because the double bond now is, whoops. That double bond now is gone. The other double bond is still here, the CC double bond. So that would be 1,2 addition that we're looking at here. The mechanism goes something like this. So the negative charge will attack this carbon here because it is partially positive due to the fact it's next to the oxygen. Fairly simple mechanism. You've seen this before. It's very similar to a Grignard mechanism. And then the H plus adds on to the O minus. Okay, so we've all seen that kind of thing before. It doesn't really make that much of a difference with lithium or magnesium there. All right. Any questions so far on the 1,2 addition? Now, let's say we change the reagent, and now what we're going to get is 1,4 addition. Now, I did have an explanation as to why this happens, and it has to do with the fact that if we look at resonance of the alpha beta carbonyl system, the 1, 2, 3, 4 system here, what can happen is that the electrons can move so that we end up getting a partial positive charge at the 4 end, right? So it's possible that we can have a negative compound come in and hit that positive charge at the end. And when we change the reagent, that's exactly what happens. The reagent we're using to achieve 1,4 addition is different. It's this one. So this is A, this is B. And you can see the different compounds here on the arrow that are causing this. So one, so it's the same group attached here, and even that is considered pretty much the same thing as what we had up here. And the copper there is just like a magnesium would be, it's positive, so whatever's attached to it is negative. So it attacks at the 4 end here, and then we get the H plus adding on to the O minus. And this creates what's called an enol. Our enols are in equilibrium. So I might change that arrow here. Enols are in equilibrium with their ketone counterparts. So there's an equilibrium here. It goes very much in the direction of the ketone when we have an enol. Enols are very unstable. Enol, double bond alcohol, enol, that's where that comes from. And then we get our product here. Okay. But the difference has to do with the reagent that we're using, whatever's on the arrow. That's what's causing the difference in the kind of product that we're getting here. Does anybody have any questions so far? I'm just about to go into an explanation as to why they're different. But does anybody have any questions so far?
Yes, so where did the double bond go? On the bottom, you are showing the arrow where the hydrogen is released and the double bond is formed for oxygen. And
Yeah.
then showing another arrow that the double bond from the
Oh, I might have missed a step here. I think I missed a step, Miriam. It was kind of an important step. I thought, I thought there was something weird about this. All right, give me a second. Let me introduce that. I think what I did was I conflated the two. Hang on. Yeah, I'm sorry. Okay. Yeah, I kind of missed an entire step here. And got the products mixed up. You know what? I'm going to start this process again here. I started the mechanism too early, went ahead of myself here. All right, let's get the product down first. And then we'll talk about that. I think that'll clear things up for you, Mariam.
thank you.
Okay, there's your product. And then we start off with the mechanism, which I kind of got mixed up with. So I started at the wrong place. There we go.
Can you say again why it's attacking at that spot?
I haven't said yet
Oh, okay.
specifically, Julie, but I will. At the present, I just want you to see that they are different and convince yourself that the products are different. Okay. That should be better, right, Mariam?
Yes. Yes.
Okay. All right, any questions so far? But you're right, Julie, I haven't explained why one is favored over the other. Okay. Let's look at why one goes one way and one goes the other way. So, and what I'm explaining to you here is very much, it's actually a very complicated kind of situation, but I'm going to describe it very simplistically, or at least simplistically as I can. And it's going to be an oversimplification. I'm just going to tell you that straight up. Okay, so in the case of the alpha beta carbonyl system, the system that's being attacked, the delta plus next to the oxygen is going to be more concentrated than the delta plus that's, or bigger if you like, but sort of tighter, if you will, than the delta plus that is on the end of the system. Right, that's the first supposition I want you to accept. The other thing is that due to the sheer size of the lithium versus the copper, so the copper is much bigger than the lithium. Since the copper is bigger, it means that the negative charge around the R takes up a larger space. I call it more diluted, if you will. Whereas the lithium one is smaller because lithium is small. And that leads to a much more concentrated charge. So the notion here has to do with hard and soft charges. So the more concentrated charge I'm calling hard, and the less concentrated or more dilute charge I'm calling soft. Now, hard charges tend to react together and soft charges tend to react together. There's a very much more complicated explanation than what I just gave you. But the point is that the lithium one, just the one with just lithium in it, is going to attack C that's directly connected to the double bonded oxygen. Whereas the copper lithium one is going to attack the end of the system, the fore end of the system, and give that product. I'm not even going to poll on this one, but I will ask if anybody has any questions. Or just for kicks, I'll poll, see how people feel about it. I don't know if I'll like the feeling, but we'll see. How do you feel about it? Five, four, three, two, one. A bunch of people didn't even vote. All right, so there are a lot of people who halfway understand. So I think part of it is because it's, it's kind of a weird explanation for something. I don't know. I couldn't go into the whole real reason, that goes right into orbitals and molecular orbitals and highest occupied molecular orbital, lowest unoccupied molecular orbital, all of that. I didn't even go into that when I talked about the Diels-Alder reaction. I let that go. If you want more about that, by the way, you can always look at the video, but I didn't want to get into it in class. It's just like I don't want to get into it here. I just want to sort of give you a sort of a quick and dirty explanation as to why that happens. But, there's a lot of halfway understanding here. Does anybody have any questions? Remember, you might help somebody if you ask a question.
I have a question about the mechanism.
Mm-hmm.
So the arrow from the double bond in the last step is taking the hydrogen. Is that
yes, that's correct?
It's not up in the air.
Well, I can do it. I can do it both ways, Miriam. I can put it to the hydrogen, or I can put it into the space between the C and the H. Either way.
Okay.
I chose this time to do it into the space, but it's still legitimate.
Okay, thank you.
All right. Any other questions about this? So as you might expect, you'll get one of these on the test, right? It'll either be the 1, 2 or the 1, 4. If it's the 1, 2, you'll get the product you see here where the attack occurs at the C connected to a double bonded oxygen. And the other one, the attack occurs on the other one at the other end, at the 4 end. And you end up getting the product you see here. All right, any questions? All right. Okay, alpha addition of ketones. So what we're talking about here is the ability for a hydrogen that is next to a C double bond O to be removed by a fairly strong base. So the hydrogens on those carbons, which we call alpha carbons, they're also called alpha hydrogens, the hydrogens on those carbons, are somewhat acidic because the negative charge that we get as a result of removing that H can possibly resonate with the C double bond O. So let me remind you of what I mean by that. This is not new, what I'm telling you here. Although some people are going to say, oh, I've never seen this before in my life. But it's possible that a negative charge in this specific position can resonate so that it ends up on the O. And if we get a double bond here, it's called an enolate. That's like an enolate ion. Enol-8. So enol, en, alcohol, 8 for the anion, enolate. So that's what I'm saying is that a hydrogen that is removed and produces this negative charge means that that negative charge then can resonate between the C and the O, which increases its stability. So because that negative charge can move between the C and the O, then it's going to be more stable. So if we throw in a strong base at low temperature, and the strong base I've chosen here is called LDA, which is lithium diisopropyl amide. Then what can happen is that the negative charge then can come in and remove the hydrogen. Now the reason that this is workable is that the negative charge here, you think, well, why doesn't it just attack the C double bond O like we did in the previous one? It's because there's too much room taken up by all of these groups that are around the N negative. So what it will do is it will take the more exposed hydrogen, this one here. It'll take this hydrogen here because it's sticking out. It doesn't have to come in and attack the C that's part of a C double bond O. So it removes exposed hydrogen. As opposed to attacking the C double bond O. That's why it's used. All right, does anybody have any questions? So let's look at an example here. So LDA, now it's low temperature here, minus 78 degrees. That also helps stop anything else from happening. And then I'll put that, and this RX is usually a bromide or an iodide. Could be a chloride as well, I suppose, but definitely not a fluoride. Fluorides tend to be too stable to react. So the attack occurs on the alpha carbon here, and the mechanism is fairly simple. So the first step here is the removal of the H to get the negative here, and then it attacks the bromide at the C that has the bromine on it. There we go. And that gives us the final product that we see here. Does anybody have any questions? Any questions? All right. Let's see how people feel about that reaction. What's your reaction to the reaction? How do you feel about it? 5, 4, 3, 2, 1. There we go. All right, that's where we're at. Does anybody have any questions? Okay. So we can get a more higher yielding process by using a different set of reagents. It does the same thing though, and this is by using enamine-assisted nucleophilic addition. So piperidine is this compound here that's got the nitrogen in it in the ring, and it reacts via the mechanism you see here in order to produce the same product. I always like the name piperidine. I think it sounds good. If I had a dog, I'd call it piperidine. I don't know how other people feel about it. Anyways, do anybody have any questions about that? You'll get definitely, by the way, you'll definitely get that B on the test. You'll definitely get on the test. I promise you. I promise you it will be there. That enamine-assisted nucleophilic addition, it'll be there. In fact, I think I might have, do I have a video for what to expect from test 4? I should have. I had one for 3. I don't know. Can anybody tell me? I guess I can take a look myself. Let's have a look. Oh, what do you know? Here it is. What to expect for test 4. So if you want to get a head start on studying the reactions, it will definitely be on there. Then you've got the means to do that. You'll find it in that video. And if you want to work really far ahead and you want to know what to study, then I recommend that you look at the problems test 4 document. Let's have a look. Problems test 4, which goes through all the reactions as well. And starting on page, I guess it's I don't know which page it is. It's like 17. So I saw 21 on the document, but 17 is the number down here, which I don't think is right, by the way. Anyway, this page here, you can go through these reactions. We got how many? 40. So if you can do these and you can do the mechanisms, and again, all the mechanisms are in a file that is located down here, test for mechanisms, 1 per page, and compare your mechanisms against the ones that I have in that file, 1 per page, then you'll be on a good track. All right, does anybody have any questions? That's about that. That's the best way to study, I think. Go on.
Just for clarification, those 40 problems have pretty much everything we need for mechanism.
Absolutely, they do.
Okay.
I guarantee it, Courtney.
Perfect.
All right. And I mean, I'll be very clear. I mean, if you look at that document, sorry, the video that I've pointed out, you'll actually see which mechanism problems are actually going to be fair game for the mechanism problems. You know, which reactions. And they are limited. There are only specific reactions that are taken for those. Is that okay, Courtney? Do you hear me?
Yes, I did. Thank you so much.
All right. Now let's continue on here. All right. So this next one, oops, wrong button. This next one takes advantage of a similar reaction here. And we've got 2 kinds of alpha addition that we can talk about if we're talking about asymmetric ketones. And by asymmetric, what I'm talking about here is a ketone that has something connected on one side, but not the other. That's asymmetric. The one I just dealt with is a symmetric one. This one is asymmetric. And it turns out, depending upon the reagents that we're using, in the first one, oops, ET3N and heat, followed by an alkyl halide, we can get the one that has the alkyl group attached to the same carbon as the R. However, if we change the conditions around and we use, let's see, I think it's LDA, yeah, minus 78 degrees. And we do the same thing, whoops. You can see that the product is going to be the one where the alkyl group is connected to the carbon on the other side. So the reasoning has to do again with what we had talked about earlier with the thermodynamic and kinetic products. Now I'm just going to limit this discussion here to the formation of the first negatively charged species. So it's going to be a similar explanation to what I had showed you earlier.
Shush.
Let's see, so this will be the higher activation energy. This one is the lower activation energy. Okay. So it's that same kind of situation as we were dealing with. Now this is going to be this anion, and that's going to be the lower one. And this one is going to be the other anion on the other side. Now it turns out that the process used to form this one requires a lower activation energy, and I'll use the LDA here. Whereas the other one requires a higher activation energy. Now the reason that the activation energies are different is that the hydrogen in this one, the LDA one, is more exposed than the hydrogen down here. So it needs a lower activation energy, and you can see that here to get to it. Does anybody have any questions about that? So that makes that the kinetic product, the one that's going to be formed at lower temperature. Low temp. This one ends up being the thermodynamic product, because it produces the more stable anion.
Do you mean product?
Yes, I do. It produces there's the thermodynamic product. It's more stable anion. Now the reason that that anion is more stable has to do with, again, the Zaitsev rule, and the fact that if you compare the two anions that we have here, the one with the negative charge where the C is attached to the R group, when it resonates, it forms a double bond that's more substituted than the one on the other side. So if you look at where the negative charge is, when it's not on the C with the R, you can see we end up getting a double bond that is not as substituted, which means that that makes this one more stable. So the bottom line is that when we're using conditions of heat, we're going to end up with the R primed group here, the one with the halogen attaching to the same R, than if we do it the other way and we use LDA, then it attaches to the other side. And we end up with two different products that way. Does anybody have any questions? Okay, if you want to take a look at that, you can ask me on Tuesday if you still have questions about that. Otherwise, we'll move on to the next topic. All right. Have a good day, folks. If anyone wants to hang around and ask me a question, they can.
Have a good one.
You too. Bye-bye.
I have a question about the last piece. So can you go back to where the carbanion was there and you were comparing?
Back up here. Yeah.
Yes. Yeah. So I didn't understand what you're saying because I'm looking at it, and at the end, the double bond. Oh, okay. So the double bond is more substituted on top.
It is on the bottom, yeah. which makes this anion, the one I'm pointing to, more stable than this one.
Huh.
And if that one's more stable, so is that one.
Yeah. Okay. Got it. All right. Thank you.
All right, no worries. Any other questions?
Thank you. Have a good weekend.
Okay. All right.